Hello friends, welcome you all to the 8th lectures on function analysis and its applications. In this lecture we will discuss the spaces LPn, L infinitian and Cx as Banach spaces. These are the contents: the space LPn, the space L infinitian, the space Cx, topological space. The space LPn. Let P be a real number lies between 1 to infinity, and LPn denotes the space of all n tuples x is equal to x1, x2 and so on xn of scalars. Then LPn is Banach space under the norm defined as norm xp is equal to summation I is equal to 1 to n mod xi power p whole power 1 by p. In other words, Cn or Rn is a Banach space under the norm this, which is denoted by LPn. Explanation: let x is equal to n tuples of x1, x2 and so on xn, and y is equal to n tuples of y1, y2 and so on yn belongs to LPn. And let alpha be any scalar, then x plus y, addition of vector, is equal to x1 plus y1, x2 plus y2 and so on xn plus yn. That is n tuples of this. Alpha x is equal to alpha x1, alpha x2 and so on alpha xn, n tuples this. We first show that LPn is nonlinear space. Let us check the all properties of nonlinear space. Since mod xi greater or equal to 0 for all I equal to 1, 2 and so on n. That is mod x1 greater or equal to 0, mod x2 greater or equal to 0 and so on mod xn greater or equal to 0. Then norm xp is equal to summation I is equal to 1 to n mod xi power p whole power 1 by p. It means mod x1 power p plus mod x2 power p plus and so on mod xn power p whole power 1 by p. Okay, each mod xi greater or equal to 0, then summation of all mod x1 power p plus mod x2 power p plus and so on mod xn power p greater or equal to 0. Then norm xp equal to summation mod I is equal to 1 to n mod xi power p whole power 1 by p greater or equal to 0. First condition satisfied. The second condition, norm xp is equal to 0 if and only if summation I is equal to 1 to n mod xi power p whole power 1 by p is equal to 0, because norm xp defined by summation I is equal to 1 to n mod xi power p whole power 1 by p. Taking the pth power of both sides, then we have summation I is equal to 1 to n mod xi power p is equal to 0. Meaning of this is mod x1 plus mod x2 plus and so on mod xn equal to 0. Modulus term always greater or equal to 0. So mod xi is equal to 0 for all I is equal to 1 to n. It is possible when each xi is equal to 0. That is x1 is equal to 0, x2 is equal to 0 and so on xn is equal to 0. So we can write x is equal to n tuples x1, x2 and so on xn, and each x1, x2 and so on xn are 0. Then x is equal to 0, 0 and so on 0, that is 0 vector. Okay, that is norm xp is equal to 0 if and only if x is equal to 0. Second condition satisfied. Third, for alpha be any scalar, then we have alpha x is equal to n tuples of alpha x1, alpha x2 and so on. That is alpha xp is equal to alpha xi, I is equal to 1 to n. Then this can be written as mod alpha power p mod xi power p. Alpha free from I, so we can write the mod alpha power p outside the summation. That is mod alpha power p summation I is equal to 1 to n mod xi power p whole power 1 by p. Okay, that is alpha power p whole power 1 by p, that is mod alpha and summation I is equal to 1 to n mod xi power p whole power 1 by p. This one can be written as norm xp. Okay, that is norm alpha xp is equal to mod alpha norm xp. Fourth condition, norm x plus y p yth norm equal to summation I is equal to 1 to n mod xi plus yi power p whole power 1 by p, because here x plus y defined the n tuples of x1 plus y1, x2 plus y2 and so on xn plus yn. So using Minkowski inequality, this can be written as less or equal to summation I is equal to 1 to n mod xi power p whole power 1 by p plus summation I is equal to 1 to n mod yi power p whole power 1 by p. That is norm x plus norm y. Hence, norm x plus y less or equal to norm x plus norm y. Thus, LPN is a normed linear space. Now, we prove the completeness of LPN. Let XM be a Cauchy sequence in LPN, and Cauchy sequence XM has n tuples as XM1, XM2 and so on XMN. Since XM is a Cauchy sequence, then for epsilon greater than 0 there exists a positive integer m0 such that for all Lm greater or equal to m0, where Lm also positive integer. Then by definition of the Cauchy sequence in normed linear space, we can write norm xm minus xl under the pth norm less than epsilon, and xm has n tuples xm1, xm2 and so on xmn. Similarly, xl also has xl, xl1, xl2 and so on xln. Then xm minus xl equal to tuples of xm1 minus xl1 and so on xm n minus xl n. Okay, so norm xm minus xl can be written as summation I is equal to 1 to n xmi minus xli power p whole power 1 by p. P. This implies that summation I is equal to 1 to n mod xm I minus xl I power p less than epsilon power p, taking the pth power of this term. We have this one, equation 1. This is the summation of modulus term of xm I minus xl I, that is mod xm1 minus xl1 power p plus mod xm2 minus xl2 power p plus and so on xmn minus xln in modulus power p less than epsilon power p. It means sum of the n terms less than epsilon power p. Thus, each modulus xmi minus xli power p less than epsilon power p for all I is equal to 1, 2 and so on n. Hence, taking the pth root of this inequality, we have mod xmi minus xli less than epsilon. xmi and xli are scalars. Okay. So, xmi minus xli less than epsilon is a Cauchy sequence in CRR. This shows that xm is a Cauchy sequence in CRR. Okay. And we know that C and R also complete. So, xli converges to the point, suppose Zi in CRR. So that xli converges to the point Zi as L tend to infinity for all I. Equation 2. Now we will show that xm converges to the point Z. Z has n tuples Z1, Z2 and so on Zn. To prove this, let L tend to infinity in equation 2, then by equation 1 for m greater or equal to m0, we have summation I is equal to 1 to n mod xmi minus zi power p less than epsilon power p, because here xli converges to the point zi using this equation 2 in equation 1. So, xli converges to the point zi. So, we can write summation I is equal to 1 to n mod xmi minus zi power p less than epsilon power p. Taking the pth root of this inequality, we have this one. Summation I is equal to 1 to n mod xmi minus zi power p whole power 1 by p less than epsilon. So, as per definition of norm, this can be written as norm xm minus z less than epsilon. Okay. As per the definition of the convergence in nonlinear space, we can say that sequence xm converges to the point z. Z has n tuples z1, z2 and so on zn. This is belonging to LPN. Hence, LPN is complete and therefore it is a Banach space. Next example, L infinity n space. Consider the linear space of all n tuples x is equal to x1, x2 and so on xn of all scalars and define the norm by norm x, that is notation infinity, equal to max value of mod x1, mod x2 and so on mod xn. This space is usually denoted by the symbol L infinity n. Then, so that L infinity n under the norm this is a Banach space. In other words, Cn or Rn is a Banach space under the norm x infinity is equal to max of mod x1, mod x2 and so on mod xn. This is denoted by L infinity n. Okay. In above example, if p tend to infinity of norm xp, then this is max of mod xi where I lies between 1 to n. This space is also called as subnorm or the maximum norm or uniform norm. Let us prove the L infinity n is a Banach space. Explanation. Let x is equal to x1, x2 and so on xn and y is equal to y1, y2 and so on yn belonging to L infinity n, and let alpha be scalar, then addition of the vector x plus y is equal to x1 plus y1, x2 plus y2 and so on xn plus yn, and alpha x is equal to alpha x1, alpha x2 and so on alpha xn. To show that L infinity n is nonlinear space, we verify the norm properties. First, since each mod xi greater or equal to 0, because modulus values of any point greater or equal to 0, then mod xi greater or equal to 0 for I is equal to 1 to and so on, and that is mod x1 greater or equal to 0, mod x2 greater or equal to 0 and so on mod xn greater or equal to 0. Means each terms with modulus greater or equal to 0. And norm infinity defined by max of mod x1, mod x2 and so on mod xn. Any max value greater or equal to 0, it means max value of the mod xi greater or equal to 0, it means each mod xi greater or equal to 0. So, norm x infinity defined by max value of mod x1, mod x2 and so on mod xn greater or equal to 0, since mod xi greater or equal to 0. Second, norm x infinity is equal to 0 if and only if max mod x1, mod x2 and so on mod xn is equal to 0, because norm x infinity defined by max of mod x1, mod x2 and so on mod xn, that is max of mod xi is equal to 0 for all I is equal to 1 to n, that is mod x1 equal to 0, mod x2 is equal to 0 and so on mod xn is equal to 0, because max value of mod xi equal to 0. Since mod x1 is equal to 0, mod x2 is equal to 0, mod xn is equal to 0, it means x1 is equal to 0, x2 is equal to 0 and so on xn is equal to 0. That is x defined x1, x2 and so on xn. So each x1, x2 and so on xn are 0, then x is equal to n tuples of 0, 0 and 0, that is 0 vector. Third, if alpha is any scalar, then norm alpha x is equal to max value of alpha x1, alpha x2 and so on alpha xn. So each term mod alpha x1, mod alpha x2 and so on mod alpha xn. So we can write mod alpha mod x1. This can be written as mod alpha mod x2 and so on. Last term mod alpha mod xn. So mod alpha max value of mod x1, mod x2 and so on mod xn. So this can be written as norm x infinity as per the statement. So norm alpha x is equal to mod alpha norm x. Third condition of norm satisfied. Fourth, let x is equal to n tuples of x1, x2 and so on xn and y is equal to n tuple of y1, y2 and so on yn, then norm x plus y equal to max value of x1 plus y1, x2 plus y2 and so on xn plus yn. We know that mod x plus y less or equal to mod x plus mod y. So each term less or equal to mod x1 plus mod y1 and this mod x2 plus y2 less or equal to mod x2 plus mod y2 and so on. Last term mod xn plus yn less or equal to mod xn plus mod yn. That is, in combined way we can write less or equal to max mod x1 plus mod y1, mod x2 plus mod y2 and so on mod xn plus mod yn. This can be written as max value of mod x1 or mod x2 or mod xn plus max value of mod y1 or mod y2 or mod yn. So as per statement, this can be written as norm x infinity and this is norm y infinity. So norm x plus y less or equal to norm x plus norm y. Hence L infinity n is a non-linear space. Now we show that it is a complete space. Completeness. Let Xm be a Cauchy sequence in L infinity n. Since each Xm is n tuple of scalars, we shall write Xm equal to Xm1, Xm2 and so on Xmn. Okay. So Xm has n tuple Xm1, Xm2 and so on Xmn. Let epsilon greater than 0 be given, then there exists an integer m0 such that Lm greater or equal to m0. So we can write norm xm minus xl less than epsilon as per the definition of the Cauchy sequence in non-linear space. This implies that max value of xm1 minus xl1, xm2 minus xl2 and so on mod xmn minus xln less than epsilon. This implies that xmi minus xli less than epsilon for I is equal to 1, 2 and so on n, because max value of this mod xm1 minus xl1, mod xm2 minus xl2 and so on mod xmn minus xln less than epsilon. This implies that xmi minus xli less than epsilon, because max value of xmi minus xli less than epsilon, it means each mod xmi minus xli less than epsilon for all I is equal to 1 to n. Since xmi and xli are scalars, then this inequality shows that the Cauchy sequence in C are R, okay, for fixed I. So it must converge to some Zi. Suppose sequence XLI converges to the point Zi as L tend to infinity. This implies that mod XLI minus Zi less than epsilon as per this definition. From equation 3 and 4 for m greater or equal to m0, we have max mod xm1 minus z1 mod xm2 minus z2 and so on mod xmn minus zn less than epsilon, because here xl1 converges to z1, xl2 converges to z2, xln converges to zn for I is equal to 1 to n. So from 3 and 4 we have this, and as per statement of norm, this can be written as norm xm minus z, where z is n tuple of z1, z2 and so on zn. Thus, L infinity n is a Banach space. The space Cx. Let Cx denote the linear space of all bounded continuous scalar valued function defined on topological space X. Then Cx is a Banach space under the norm f is equal to supremum value of f belonging to Cx mod fx such that x belonging to x. Okay. So we can prove this easily as above example. Here function f belongs to Cx. Then vector addition and scalar multiplication of function defined by this way. Suppose f plus g, where f and g belonging to Cx, then f plus g x equal to fx plus gx, and alpha f x equal to alpha fx. We now show that Cx is nonlinear space. Since mod fx greater or equal to 0, because this is the modulus value always non-negative. So modulus fx greater or equal to 0. We have norm f is supremum value of mod fx such that x belonging to x greater or equal to 0. Okay, because mod fx greater or equal to 0. Hence norm f greater or equal to 0. Second, if norm f is equal to 0, if and only if f is equal to 0 function, because norm f is equal to 0 if and only if supremum value of this is defined by norm f, that is this one equal to 0 also. Then supremum value of mod fx is equal to 0, it means mod fx is equal to 0. Mod fx is equal to 0, it means fx is 0. Fx is equal to 0, it means this is a 0 function. That is norm f is equal to 0 if and only if f is equal to 0 function. Third, if alpha is any scalar, then norm alpha f defined supremum mod alpha fx, that is here defined norm f is equal to supremum of fx. This f, that is fx. Here norm alpha, that is defined supremum alpha fx. Here alpha fx, meaning of this alpha fx. So this can be written as alpha fx. Mod alpha fx can be written as mod alpha mod fx. Okay. Here supremum value of mod fx, where x belonging to x, alpha free from the x, so we can write outside the supremum. Mod alpha supremum of mod fx such that x belonging to x. This term can be written as norm f as per this statement. That is norm alpha f is equal to mod alpha norm f. Fourth condition, let f and g belonging to Cx, then norm f plus g can be defined as supremum value of mod f plus gx such that x belonging to x. Here f plus gx is defined by fx plus gx. So we can write norm f plus g is equal to supremum value of mod f plus g x. We know that mod x plus mod y less or equal to mod x plus mod y. So this term can be written as less or equal to mod fx plus mod gx. That is, this term can be written as less or equal to supremum value of mod fx plus mod gx such that x belonging to capital X. This is also less or equal to supremum value of mod fx plus supremum value of mod gx for all x belonging to x. As per the statement, we can write this norm f and this one as norm g. Hence, norm f plus g less or equal to norm f plus norm g. Hence, Cx is norm linear space. Completeness. Now we prove that Cx is complete. Let Fn be any Cauchy sequence in Cx, then for a given epsilon greater than 0, there exists a positive integer m0 such that mn greater or equal to m0. This implies that norm fm minus fn less than epsilon. This is less than epsilon. This implies that supremum mod fmx minus fnx such that x belonging to x as per the statement of norm. Okay, so supremum value of mod fmx minus fnx less than epsilon. This implies that mod fmx minus fnx less than epsilon. But this is a Cauchy condition of uniform convergence of the sequence of bounded continuous scalar valued function. This is. Hence, the sequence Fn must converge to a bounded continuous function f on x. Therefore, Cx is complete and hence it is a Banach space. In this lecture, we have discussed the spaces Lpn, L infinity n and Cx as Banach spaces. These are the references which have been used in this lecture. Function analysis, Dover publication written by George Beckman and Lawrence Naresy. Second, Introductory Function Analysis with Application, John Whaley and Sons, written by Erwin Krejcik. Third, Function Analysis, New Age International Publishers by V.V. Lemieux. And fourth, Function Analysis, Tata McGraw-Hill, written by Waterrudin. Thank you for your attention.